Hello and welcome to this short video. Here we will go really at the detailed number level and calculate evaporation rates on a liquid surface, including Stefan flow. The situation is marked here as follows by this image. We have a lake, and from the lake there is evaporation taking place, so we have transfer of water vapor into the ambience. The question is, how can we describe the problem? I am assuming here that air and water have the same temperature, but before we go into the details, we have to ask ourselves, what is the driving mechanism, and is there a limitation in any of this? For example, here we have the question, does the mass transport limit the problem? So is the driving potential maybe limited by the ambient being too humid, so that we can't get, no matter how much heat you apply to the liquids, anything into the air? Or is heat transfer or heat transport the problem? So that's something we need to think of in the beginning, and then go about this. In our case, we do not have the heat transfer as a problem, because we assume that the water temperature is not changing over time due to how big the reservoir is, so it remains, although evaporation takes place at 25 degrees centigrade. Now, that's what I just said. That's highlighted here by the green. Mass transport, we need to think about ambient conditions, and the assumption, as I said, that we put forward air temperature and water temperature given remain constant, and the water temperature does not drop. Now, if you want to do the calculation, we need to determine the driving potential. So, as in our derivation for derivation for the Stefan flow, we assume that the water can leave the liquid, but air cannot enter the liquid. So the water surface is only permeable for water, so it's a semi-permeable surface, and this leads then to this expression for the area-specific mass flow rate of water or water vapor. Now we need to understand the mass fractions, so I have values for those in order to do the calculation for the mass flow rate. So how can we determine this? Well, the water mass fraction in the air depends on the saturation level. At the water surface, we can assume that the air is fully saturated, so relative humidity is 1. And the temperature of the air and water have been set equal here. So I need to assume the humidity in the air, and that's already indicated here on top. I'm assuming that the air humidity is at 50%. With that, we can move forward and do the calculation. And we can determine, or we can relate the mass flow rate to the mass transfer coefficient. And for that, we need to do a few calculations. How can we do that? We assume that the Lewis law is applicable, and then this means we can determine the mass transfer coefficient G from the heat transfer coefficient alpha. How do we do that? Well, we first have to request that as a boundary condition, Prandtl has to be about the same value as Schmidt, or in other words, the thermal diffusion has to be similar to the mass diffusion. Now, we need to go through different steps. Before we go through the calculation procedure, what do we describe? We will describe diffusion of water and air. The water surface, as the phase boundary is put at x equals 0, the interface is permeable for water only, as I said, so it's a semi-permeable phase interface, or we talk one-sided diffusion. Now the calculation procedure. We'll first have to determine the average heat transfer coefficient, then the mass fraction somewhere above the surface, the mass fraction at the interface, and the mass fraction in the far away from the surface. We have to take then the Lewis law to determine the mass transfer coefficient, then the area-specific evaporation rate, then the amount of heat required to do the job. And then we can see if there is a limitation which we did by putting the corresponding boundary condition actually not into account, but we shall see later. The average heat transfer coefficient, how do we get that at the surface? And average means across the surface. Well, we use a correlation from our chapter 5, heat transfer correlation 6, that states alpha average times length divided by lambda. That's the Nusselt number is this here. So we have to determine Reynolds and Prandtl in order to solve it. The values that we have to take into account for calculating these are tabulated in the manuscript, lecture manuscript. However, our temperature is not called out here, so it's 25. This means we have to take the values of 20 and 40 and do an interpolation. Well, this leads then to values for the viscosity, density, specific heat capacity, thermal conductivity, and finally then Prandtl number be calculated from those at 25 degrees centigrade. Then we put that into Reynolds number as the length. I take here the length of Lake Constance. That is the lake considered in our problem here. And it only comes in by this dimension or by the surface area. So all other considerations in this example are not specific to Lake Constance, can be any lake, could be a small water puddle. So you just have to make sure you pick the correct length and surface area. So Reynolds number is a fairly high value, and this could lead to a very high heat transfer coefficient when we look at this. And Nusselt number then is also very high. However, we calculate alpha, we have to divide this by length. So alpha is Nusselt time lambda over length, and length 63 kilometers. So we get to roughly 4 watts per meter squared in Kelvin. And remember back at the conduction lecture videos, there we said here the convection, that's natural convection, and we have single digit to maximum 20 watts per meter squared in Kelvin for the heat transfer coefficient. So this fits well within this envelope. It seems like it's a good pick. In the past, I used to do this example without exact values. I just took 10 watts per square meter in Kelvin. So now let's have a look at what comes out if I take this value determined from the above correlation here. Let's determine then the mass fractions. So I need first to derive an equation which relates mass fractions to some problem parameters, and then I can determine the mass fractions at the points of interest. So mass fraction here is mass of water divided by the total mass. That's air and water, or water vapor, air. Both I will calculate from the universal gas law. So I take the same volume in here, the specific gas constants. I had said that the temperatures are the same. So this expression when setting this in here can be simplified, same temperature, same volume, so I get the ratio of partial pressure divided by the corresponding gas constant to be taken into account. I can even more simplify it because the air pressure can be expressed by the total pressure, which is then 1 bar minus the saturation pressure of the water vapor, and then I only have the water vapor partial pressure in this equation. So you see here now an expression for Xi water vapor, and this carries the molar mass of air, molar mass of water, and the partial pressure of water vapor. And if you now calculate this to determine the water vapor surface fraction, then we know that's at the saturation pressure. The saturation pressure we have to take either from a table or to calculate that. In our case, in the appendix, we have here a table, but not of values. We have an equation listed. That's the Antoine equation, which carries 3 constants and the corresponding temperature for which you want to estimate that. And you see down here, there is for waters in the temperature range between 1 and 100 degrees centigrade, these constants. So we use this and can now calculate the saturation pressure at 25 degrees centigrade as 0.03166 bar. With the corresponding molecular weights of air and water vapor, we get to the value for Xi H2O at the surface. That's 0.0206 kilogram water per kilogram air. And we can do the same for the water vapor fraction in the air. We assumed we have 50% relative humidity. So the value of the partial pressure to the saturation pressure is 0.5. And if we put that down, we can from this calculate this value here, put it in the equation, and end up with Xi H2O far away from the surface is about half of the value that we determined for the surface. The mass transfer coefficient then can be calculated. For this, we need to look at the Lewis law for all gases. And we had stated when we have strict analogy that Sherbet over Nusselt is a ratio that can be expressed by Schmidt and Prandtl. And we came then up to an expression that mass transfer coefficient divided by heat transfer coefficient divided by specific heat capacity is Schmidt over Prandtl by n-1. If heat and mass transfer are strictly analogous, we get here a case where Schmidt and Prandtl are almost equal, so we get a 1 on the right-hand side, or we can express G as alpha divided by Cp. Now we have calculated alpha average, we have determined Cp, so we can calculate the mass transfer coefficient, taking the values that we have here, and Cp is given even in the problem, and G as alpha divided by Cp then is roughly 4 times 10 by the minus 3 kilogram per second and meter squared, or 4 grams per second and meter squared. Now, what is then the evaporating mass flow rate? So that's G times driving potential, and you know what we divide here by is for the Stefan flow, and if you put that in, replacing G by alpha divided by Cp, we get to these values, and finally it's roughly 4 times 10 by the minus 5 kilograms per meter squared and second. So a few milligrams per meter squared and second. Now, if you take into account the surface area, and the surface area will be the entire mass flow rate is the area specific times the area. The area is 536 square kilometers, and if you put in this large number, we end up with 21,000 kilograms per second that we get, or 21 tons per second over this large lake. And which amount of heat is required for this? Well, the amount of heat is water mass flow rate times enthalpy of vaporization. And for this, I just took 2,500 kilojoule per kilogram. The value is from above here, and we end up with 53 megawatts as the amount of heat required. And now we could go further and look into solar radiation or heat from the ambient. Is this supplied to the lake? But I don't want to go that far and close the problem here. I just wanted to show you what are the individual steps to go about. And this leaves me with a few questions that you should be able to answer here. How do we calculate the mass fractions? Under which conditions does the Lewis law apply? How is the mass transfer coefficient calculated using Lewis law? Of course, by the heat transfer coefficient. And then how do we determine how much mass of the lake water does evaporate? Thanks for listening.